The idea here that CUDA implements, both in terms of the hardware architecture and then in terms of the software development environment that we have, is that of heterogeneous computing or heterogeneous processing. The implementation of this heterogeneous processing is the fact that we will be able to utilize a uniform integrated development environment and integrate within this integrated development environment two different compile platforms. One that will target or compile programs and the executable functionalities to run on the CPU side, and as well as a compiler that compiles and creates the binaries and executables that will be then deployed onto our GPU side. To simplify, referring to these two different processing units, we will call the CPU side both the CPU code and the CPU hardware architecture itself the host, and then the GPU side, both in terms of the GPU side code and the GPU architecture in terms of hardware, we call it the device. And CUDA compiler that we use is called CUDA C, or NVCC, NVIDIA C compiler, that is integrated within either, if you use Linux with the GCC compilers, or on Windows, it's going to be integrated within your Visual Studio IDE. So we will write programs, and you will see that the programs are going to look very much like C code, both in terms of the host code and the device code. And what we will do is that we will tag the pieces of code that needs to be compiled and run on the device with the device specifications. There are keywords and tags that will tag the piece that will be compiled and run on the GPU. And we just leave the host code just as a plain, straightforward CPU code. So basically, our programs are C++ programs. They look very much like your generic C++. In fact, they are C++, or rather C. And when compiled, parts of the program will be deployed and run on the CPU. Parts of the program that need to be run on the GPU, they're going to be compiled as device code. There's a certain limitation here that you need to be aware of before we get into it, and we will get into it, is that your functionalities that are device side functionalities, they have to be all integrated. So for example, we cannot have memory units on the host and try to access them within the device code, and vice versa. You cannot have memory units on the device and try to access them from the CPU side or the host side code. Also, you cannot have functions on the CPU side and try to invoke the functions on the device side. But you can invoke functions on the device from the host, and that is in terms of essentially implemented with a function that's called a kernel invocation. So we can write, in fact, our functionalities, our device functionalities are going to be run as functions on the device that then we can use and invoke them as kernel executions. And we'll see this in a little bit later. So the idea here is that our attempt at heterogeneous computing here is a host device processing mechanism. So how does this host device processing work? We will have general overall program functionalities to be host programs, and basically they will be the CPU functionalities here. What the CPU side code or the host side code will have is it will have access to the host side memory. So that would be your DDR memory that you in any kind of C programming, you will basically use in the form of pointers, variables, arrays, objects, and so forth. And the main functionalities of your program is going to be implemented within your CPU code. So the main function and any other functionalities that are the generic infrastructure of your program is going to be on the host side. On the CPU side, basically you will write your code within the same file. We can have a separate file that you associate, and you just tag the pieces of your functionalities with the CPU, with the GPU or device specification tags. And so those will come in the form of, the majority of them will be in the form of kernels that you will invoke. And these kernels effectively take care of a thread of execution that will be implemented in program. The way that the two device and host processing units communicate with each other is in the form of passing the information back and forth through the so-called global memory. Global memory is the memory unit that is located on your graphics processing unit, and it is directly connected through your PCIe bus to the central processing unit, and you will be able to pass data and information back and forth between the device side code and the host side code through the global memory. So a typical processing cycle in a program, in a CUDA program, looks as the following. Basically, you will have a piece of functionality that is created on the CPU side, and you will ask the allocation within your CPU or your host code for storage units. And this means that you allocate storage units on both GPU and the CPU side on the host. So the host allocates memory on CPU, and also it allocates memory on the GPU side. And so basically your storage units are going to be created. Then if the GPU needs to receive data from your CPU, the CPU code also goes and functions as essentially copies the data from the GPU memory from the CPU memory to the GPU memory. Then the CPU launches the kernels that are now device side codes. So these kernels are essentially on the device side. So CPU invokes those kernels on the GPU. Once you're done, the results can be copied back from the GPU on the CPU. So the CPU, basically the CPU or the host side functions and programs essentially allocate memory, copy the data from the CPU to the GPU so the GPU could start processing, invoke the GPU side code, and then let it go. And then the GPU side code works, and when done, you will be able to go and retrieve the information and the data back from the GPU and copy it on the CPU side. So this typical processing cycle is what is going to happen on the CPU side, and that's what the building blocks are. Now, what is important is this third item here, and the kernels. These are essentially the things that run on the GPU. So CPU will be able to invoke them and call them up, but once they're invoked on the GPU, CPU will have absolutely no control over their execution. And the GPU at this point will go ahead and take care of allocating, running the threads in thread blocks and warps and associating them with the streaming multiprocessors and whatever it needs to do to execute the code. So at this point, our job is to define our computation that needs to be done on the GPU, outsource it on the GPU, and then perform the bookkeeping processes on the CPU side. So the big idea is to look at our program and try to look at it and format it in a parallel pattern, a parallel format that essentially look like a serial program that will start and has a thread of execution, and it will be basically essentially, if you look at it as one single thread, if it were to run as one single item, it would be a serial program. Then we would wrap this serial program in a shell, in a unit, and we call this a kernel. Then we have the kernel to be associated on the GPU, and we'll see how we can associate that. Basically, your kernel is going to be essentially a function in C, and we tag it as a GPU side function that then will be invoked and will given to the GPU, and also instructions to the GPU as to how many of these and in what kind of format we want them to run. If we were to run this kernel on the CPU, it would just run once. And as opposed to having this kernel to run once on the CPU as a part of one function call, we make a specialized function call. And that function call is called invoking the kernel on GPU. And there's a special format for it, and we'll see how it can be done. And at that point, the CPU will invoke the kernel and handle this kernel to the GPU with how many and in what kind of configuration it wants it run, and then the GPU will run many copies of this kernel as separate threads of execution. And this is where that fork pattern comes in. Essentially, your CPU forks a bunch of processes, and to each of those processes will give a kernel to handle with an associated ID. We as programmers can set the number of threads, and this is the core of parallel programming on GPU. The way that we associate the kernels once we define our program and its way of parallelization and execution within the kernel, then we will be able to run a bunch of these together, a bunch of these in the form of threads, and we can specify how many we need to run. So again, looking back at what we talked about, the performance measures, we know that GPUs have a great many specialized processing units, which we call them simple processing units, simple processors, and they're formatted in a mechanism in terms of hardware that will fully utilize their parallelization, and we call those streaming multiprocessors. And as such, we know that CPUs are good at efficiently running and handling a large number of programming threads. So GPUs can handle efficiently lots of thread executions. Unlike any other programming methodology so far, the best way to utilize your graphics processing unit, once you exploited the parallelization patterns of your program and algorithm, is to run a large number of these threads on your GPU to ensure that there are a lot of tasks for your GPU to do, so that you won't have your GPU processing units idle, as with the example of a bus going at half capacity or the third capacity and so forth. So later on, when we get into the efficiency and optimizations of our programming, there will be an idea that we'll look at, and that's called occupancy. And the occupancy tells us how many of our processing units within our graphics processing, how many are CUDA cores have been given tasks to do, and how many are idling, or the percentage rather. And so when you see that you have a low occupancy, that means that there are a lot of threads that are not being associated to graphic units, or rather to your cores and processing units. And so basically you're not utilizing your hardware architecture to the fullest extent. So the way to go in CUDA programming is to make sure that we have a large number of threads, and that these threads are designed in such a way that at any given time a large number of our processing cores are executing a large number of threads, and we don't have many processing units waiting for the completion of a few threads. And then the idea, of course, will be running all these threads in parallel. And this is what gives us the efficient throughput. If we create a large number of threads and then run them one at a time, we're not really exploiting the parallelization in our hardware. So the idea then would be, once you have a large number of threads, to be able to also ensure that all these large number of threads are running in parallel, as opposed to everyone just waiting around for others to finish their jobs. So the two tasks that we have to accomplish is to create a pattern and a mechanism that we could design that can be parallelized and exported into or created into smaller threads of execution, and then associating and enabling our graphics processing unit to run these threads in parallel. Let's take a very simple look at a very simple example. And I'll start by writing it in a serial code, and then we'll see how it can be run in just one execution unit. And then what are the patterns that we can exploit in terms of running it on the GPU side, and how we can parallelize it. Basically, extending its loop invariance and then outsourcing it and making it into a loop pattern that is parallelizable because of the loop invariance, and we talked about this in one of the previous lectures. And then we'll see at both the serial side code and the GPU side code. From this point, then I'll switch this lecture into a programming lab, and then we'll do our very first CUDA program, and then we'll dissect this CUDA program into its components, and we'll see how they work. So the problem I'm trying to address here is calculating the cubes of items in an array. Let's suppose that we have an array of elements, say 64 of them, and we want to take these as input. And then in the next unit we'll talk about communication patterns, and we'll see what this pattern is called. We take this array of inputs, and then the result we're interested in is the cube of each of these elements. So the idea is go over every single one of these items in the array and take the value, multiply it by itself 3 times, and then store its value either back into the array, or if you wanted to keep the original copy, we create a new array, and then for each unit in the array, we multiply the unit by itself, and then we copy it into the output array. So here's how our serial code would look like. Basically, in C, we're going to have a loop that runs for number 0 as an index to 64, rather 63 here. For each number, we take the output at that location, and it's going to be equal to the input at that location times itself 3 times. So we look at the first element, that would be input 0, and then we multiply it by itself 3 times, and then we associate that result to output 0. So input 1 will be multiplied by itself 3 times, and so the output 1 will be input 1 cubed, output 2 will be input 2 cubed, and output 3 will be input 3 cubed, and so on and so forth, and we run this for 64 times. So the serial code basically would look like this. We have a loop. The loop starts at the location 0, goes all the way through to location 63, takes each input value at that location, multiplies it by itself 3 times, and puts it in the output location value. Only one thread of execution is required here, so our code starts at some point and then loops for 64 times and then finishes. So this area here is going to be my for loop. Notice that each thread of execution of the loop, each loop iteration, is independent of previous or the next iterations. And this is the loop independence that we talked about in the last unit or the unit before that. that if you have a for or while or a repetitive process, it takes over iterations. And if the iterations are not dependent on each other, so for example, here we take input at location I and multiply it by itself instead of multiplying by its previous or its next location. Then we have the loop invariance. We have the iterations that are basically independent or loop independence that are independent of their previous or the next generation. And with this, if you look at this single piece of code, there's nothing we can do to parallelize this piece of code because we have 64 items, and in order to process every single item, we would have to go over every single unit within the array. And so there's no explicit parallelism associated with this pattern. But there's a great deal of parallelism inside of this pattern, specifically because of the loop independence. And that is, instead of having a loop that goes and executes the same piece of code 64 times, but in serial, why don't we create 64 processes and give every single one of those processes a unit to process? This way, the step complexity of that process will be just 1 instead of 64 here in this case. And if that were the case, and if we could run these in parallel, then in one step we will be done with the entire calculation, as opposed to having to run 64 steps to finish up our calculation. So let's try to move this code into the GPU. Now, again, as I said, there are 4 steps that we need to address. And those 4 steps is to allocate memory units. So item number 1 is here. To copy data back from this host memory to the CPU, then to the GPU, then to launch our kernels and invoke them on the graphics processing unit. And when we're done, which I haven't specified here, is to copy back. So I'm going to write this piece here, is to copy our code, our results actually, back to CPU. So on the CPU side code, we don't have any association directly with the graphics processing unit or the GPU, aside from calling up the GPU side functions and then taking care of the bookkeeping items like copying data to and from the memory. So actually number 2 and number 4 both are in here. On the GPU code, our code looks very much like a serialized process. We will create a functionality that expresses the process that we have in mind. In this case, we have out, which is equal to in times in times in, 3 times input. And it doesn't really have any degree of parallelism associated with it. So the GPU code, as far as its look, is basically like a serialized process. However, notice that in section number 3 here is where we invoke the code from CPU, we invoke the GPU code. That is where we specify our degree of parallelization. And we'll talk about how we do this next. And that is when we invoke the kernel, when we invoke the functionality that we want to run on the GPU, we will tell our GPU that this is the functionality I want you to take care of, and this is how I want you to take care of it in terms of how many items and how these items should be created with respect to each other that would take care of the functionality and the process. Now, as I said, to specify the degree of parallelism, which is this item here, to launch the kernel and specify your degree of parallelism, we would invoke the threads of execution on the CPU side. So where is the parallelism? The parallelism comes in when you launch your parallel threads, and we call these parallel threads kernels on the CPU, and they are the processes that are going to be run in parallel on your GPU, and your GPU hardware will take care of it. So CPU will ask the GPU to launch a number of threads, and each thread to basically run the entire kernel function independently of any other threads that are going on. And if there are any kind of data dependence, then the programmer, we would have to implement that dependence functionality in terms of barriers, synchronization, and shared data pattern communications with each other inside of the kernel itself. So the CPU code of invoking a kernel would look like this, and we'll run this in a program in a little bit. But what you will have is we will have to have had specified a function, just like a C++ function, with all the things that are associated with a function call. We need to create a function and then make the function call in our CPU code. And for example, here I called this cubes kernel. And then as you see, this cubes kernel also gets a number of parameters and arguments. And these arguments are actually GPU memory units. So both these D sub input and D sub output are memory on the GPU side, and we'll see how we can do this. And then as a part of this kernel invocation and kernel call, we basically specify the degree of parallelism as a part of our function call with these three little brackets. Three little chevrons, left and right chevrons. And what this means is that the CPU will ask for a kernel on the GPU to be run on a specific memory locations that it needs the GPU to run the functionality, and the pattern of parallelization. Essentially, how many kernels in what kind of format or configuration do we want them run. And once that is done, then the execution of these kernels will be out of our hands. The GPU at this point will take these kernels with whatever we ask them, whatever configuration and specification we ask, and then it will associate them to streaming multiprocessors, and then it would run them independently of each other in parallel, and then we will be able to get the results that is created. Now, before we go further, let's take another look at our serial code and the kernel GPU code side by side. But again, let's take another look at how on CPU we call and invoke the kernel. So see the invocation of the kernel function name, the pattern of the kernel threads that we want to run, and the arguments of the kernel. Now the serial code was very simple. We had a loop that runs over 64 items of the input, and for each output item, it multiplies the input item at that location and copies it into the output function. How does the kernel look like? The kernel code essentially looks exactly the same as the serial code, and specifically it's this line of code that is of huge importance. This is the functionality of my kernel. The kernel basically embeds this piece of functionality. Take the input, cube it, create the output. Now, to see how it works is that, as I said, our kernel embeds the functionality, and then the GPU runs kernels in parallel. So what we need the functionality to be is to multiply a value from the input array by itself 3 times, and then copy it into an output array. But what we did is we actually, instead of running a for loop for each item, we basically create a bunch of items, a bunch of kernels, each of which in charge of multiplying a value by itself 3 times. But then we associate each of these kernels to one of the items. So we call these item indices basically. And so the serial code is in charge of running one unit of operation 64 times on different values of data. The kernel code, on the other hand, is in charge of performing the same operation, multiplying an item 3 times with itself. But every time it's run, or every kernel that's run, is given an independent separate value to multiply 3 times by itself. So for example, the kernel, and so the index that we have here, we read that index from the kernel or the thread index of our calculation. So the kernel number 0 or thread number 0 basically multiplies inputs at location 0 3 times and creates the output at location 0. Kernel number 2 or thread number 2 or multiplies the input at location number 3 or number 2 and calculates the value. Kernel number 63 or basically multiplies item number 63 3 times and creates the result. So basically the difference is your serial code starts here and then runs 64 times and then finishes up. So this will run 64 times, this piece of code. Your kernel execution, on the other hand, basically will create 64 kernels. And remember, when I put in the triple chevrons 1, 64, what I did is I asked my GPU to create 64 kernels, 64 threads, and then run them. So it's going to create 64. Instead of running the same operation 64 times, it's going to create 64 threads. And I'll basically write these with wiggly lines. Okay. So thread number 0, thread number 1, thread number 2, thread number 3, thread number 4, thread number 5, and so forth. So each of these is basically my thread index. Then, so each of these is in charge of one item, one unit, to multiply 3 times and then create the output. And once you're done, then you basically, all your threads will exit out at the end of your thread execution, or rather the kernel execution. Let's take a look at the anatomy of a kernel and see how a kernel is created before we actually go and do this implementation. A kernel will have it's a function, so in C it has to have a valid function name. As a part of data patterns that you use, you would have to associate and pass arguments to your kernel. And these arguments can be passed as either variables or pointers to memory that is allocated and associated on the GPU. So in our case of multiplying 64 values, what I did is I created pointer variables, and I'm passing the pointer, see the star here? This is basically a pointer, and I'm passing the pointer variables to my kernel to execute. The kernel is not creating any output, so it's basically an output data type of void. And finally, the first line is the global tag. So basically it's 2 underscores, the keyword global, and 2 underscores. There's no space in between them. This keyword tags this function as being a GPU code. So this function, when you put underscore global, underscore, underscore, global, underscore, underscore before a function, that tags that function as a kernel that will be able to run on the GPU and then you can invoke this kernel in your host code later on whenever you need to do that. When you do this, then every single copy of this cube's kernel, every single copy of this kernel will be given an index, and that index can be in the form of a complex block index in 3 dimensions and thread index in 3 dimensions. We'll talk about how these indices are created. But every single one of these copies of this function or this kernel on GPU, when they are invoked, they will be given a unique identifier, a unique index. Then from that point, you can use that index in any kind of patterns that you want to be able to write the functionalities of your program. So basically, then, for example, in our case here, is I wanted this kernel to be passed one of the 64 elements in the array. So I use the kernel index as the index of the element that that kernel would be responsible for. So in memory, what I have is an input memory that is made of 64 items. So item number 0, 1, 2, 3, and so forth to 63. So this would be my input. And then I have an output array of the same size, 0, 1, 2, 3, and so forth. So what I'm going to do is that when I have a bunch of kernels, so kernel number 0, kernel number 2, or rather thread number 0, number 1, number 2, what I'm going to do is that I'm going to associate thread number 0 with the index of item number 0, thread number 1 with the index of item number 1, thread number 2 with the index of item number 2. So in effect, thread number 0 will basically work on the input number 0 and creates the output number 0. Thread number 1 will work on the input number 1, and then it writes the results into output number 1. So thread number 2, thread number 3 basically takes the input 2, calculates output 2. Thread number 3 takes the values from input 3, calculates, writes in output 3. Thread number 61, thread number 62, and thread number 63, which will basically work. Sorry, this is 63. Work on each item independently and writes the values independently. Later on, we'll see this pattern is called the map pattern, when you have a bunch of threads and they're responsible for working on one unit of data and writing into one unit of data, basically a one-to-one mapping relationship between your input and output, which is the simplest pattern of communication in parallel communication.